Welcome to this explainer, everyone. Today, we're diving into a real micro to macro journey. We'll start way down at the invisible, jiggling molecular level and then zoom all the way out to see how that tiny energy causes massive real-world consequences around us. Whether you're an engineering student or just curious about the invisible physics governing our daily lives, you're going to find this incredibly useful. Here is our roadmap for today. We're hitting 3 main stops. First, defining temperature and heat. Second, the principles of heat transfer. And third, the thermal expansion of matter. Let's get into it.
Section 1. Defining temperature and heat.
To really grasp this, we've kind of got to forget what we can see with our naked eyes. We're going microscopic. When we talk about temperature, technically, it's the degree of hotness or coldness measured on a specific scale. But what actually makes something hot? Well, it's literally just molecular activity. Down at that microscopic level, temperature is simply a measurement of kinetic energy. It's just how fast the molecules in a substance are moving or vibrating or jiggling around. So as those molecules get more agitated and move faster, boom, the temperature goes up. It's really that simple. Now, this is absolutely crucial. Understanding the difference between temperature and heat. People use them interchangeably all the time, right? But in physics, they are completely distinct concepts. Temperature is what we just talked about. It's a measurement of that molecular kinetic energy right at this exact moment. Heat, on the other hand, is the actual transfer of that energy between bodies because of a difference in their temperatures. Heat is the flow. And since it's an energy transfer, we measure heat in units of work or energy. You'll see it measured in joules, the standard SI unit, or in calories, or BTUs, which stands for British Thermal Units. Okay, take a look at this highly specific fraction, 1 over 273.16. This is actually how we define the Kelvin, which is our standard SI unit for temperature. 1 Kelvin is precisely 1 over 273.16 of the temperature of the triple point of water. Now, if you haven't heard of the triple point, it is this incredibly delicate, exact temperature, specifically 273.16 Kelvin, or 0.01 degrees Celsius, where water literally exists as a liquid, a gas, and solid ice, all at the exact same time in perfect equilibrium. It's wild, but it gives us this rock-solid, unchanging physical anchor for our temperature scales. Moving on to part 2, principles of heat transfer. So we know what heat is, but how does it actually get from point A to point B? This everyday kitchen setup is actually a brilliant way to see the whole picture at once. We've got a pot of water boiling on a stove, and believe it or not, all 3 methods of heat transfer are happening right here at the exact same time. You've got conduction traveling up the solid handle, convection circulating the water inside the pot, and thermal radiation radiating out from that glowing burner. Let's break these down one by one. But before we dive into the specific mechanics, we absolutely have to establish the golden rule of heat flow. Heat will always, literally without exception, transfer from a hotter body to a colder body until they reach the exact same temperature. Areas with higher kinetic energy are always going to dump that energy into areas with lower kinetic energy. And the second they equalize, that's what we call thermal equilibrium. First step is conduction. This happens when 2 objects at different temperatures are in direct physical contact. Since they're touching, the hyperactive, fast-moving molecules of the hot object physically crash into the slower molecules of the colder object. It's kind of like a microscopic game of billiards. The fast molecules transfer some of their energy to the slow ones during these collisions. Because it relies on things bumping into each other, solids, especially metals like copper or aluminum, are fantastic conductors. Their molecules are packed super tight, making those collisions highly efficient. Next is convection, and this is the heavy hitter for transferring heat in liquids and gases. Convection is all about fluid circulation, and it's totally driven by changes in density. When you heat up a liquid or a gas, it expands. Its volume goes up, which means its density goes down. It becomes buoyant. So that warmer, lighter fluid rises to the top, while the cooler, denser fluid sinks down to take its place near the heat source. That creates this continuous rolling cycle we call a convection current. It's exactly where the old saying, hot air rises and cooler falls, comes from. And the third method is radiation. Now, conduction and convection both need some sort of matter to transfer heat, right? Radiation doesn't. It requires absolutely no physical contact and no medium at all. Heat just travels straight through empty space as thermal radiation, which is an electromagnetic wave moving at the literal speed of light. I mean, this is exactly how we can feel the heat of the sun on our faces, even though there are millions of miles of freezing, empty vacuum between us and it. All right, final section, part 3, thermal expansion of matter. We've seen how heat moves, so let's look at what actually happens to matter when it absorbs that heat. This is where we run into some very real engineering headaches. Remember how temperature is just the kinetic energy of molecules? Well, when you pump thermal energy into a substance, those molecules get energized and start vibrating violently. As they shake around, they essentially shove each other further and further apart. The macro result of all that microscopic shoving is that the whole object literally gets bigger. It expands in all directions. And naturally, when it cools down, they slow down, pull back together, and the substance contracts. To see how this expansion really plays out, we just need to look at the three everyday states of matter: solids, liquids, and gases. Because they're built differently. Solids are rigid and tightly packed. Liquids are fluid, and gases are super spread out. They each react to thermal expansion in their own unique way. If we were handing out medals for expansion, gases would absolutely take the gold. Since gas molecules are already so loosely connected, when they get hot, their volume explodes, expanding perfectly in proportion to the temperature spike. Liquids take silver. They expand noticeably and will push out to take up more space in whatever container they're in. Solids get the bronze. Because they're rigid, they expand the absolute least, but they definitely still expand slightly in every direction. Let's look at what this means in the real world, starting with solids. Even though a solid only expands a tiny bit, the physical forces involved are massive. If engineers ignore this, it's a disaster. It's exactly why railway tracks have those visible gaps between the steel rails. The metal needs room to expand on a scorching summer day. Otherwise, the tracks would literally buckle and derail a train. Same goes for those overhead power and telephone lines. You ever notice how they hang with a bit of slack? That's on purpose. When winter hits and the metal contracts, that slack ensures they don't just snap under the extreme tension. Liquids expand quite a bit more, which forces industries to get a little creative. When you're pumping water or chemicals through giant industrial pipes, engineers actually have to build in these big U-shaped expansion loops every so often. As the hot liquid expands and pushes outward, those loops physically flex to handle the extra volume. If they didn't, the pipes would just burst open. You've actually seen this in your own fridge too. Beverage companies always leave a little pocket of air, called headspace, at the top of a soda bottle. If that drink gets warm in transit, the liquid needs room to expand without blowing the cap off or shattering the glass. Finally, we have the huge expansion of gases, and honestly, we use this to do some pretty cool stuff. A hot air balloon is the classic example. You blast the burner, heating the air inside the balloon. That gas expands, its volume shoots up, its density drops, and suddenly that warm, light air lifts the whole basket off the ground. Or think about something as basic as baking bread. The heat of the oven causes little pockets of trapped carbon dioxide gas in the dough to rapidly expand. That microscopic gas expansion is literally what forces your bread to rise and get all nice and fluffy. So we've traced the micro vibrations of temperature, the flow of heat, and the macro expansion of matter. But before we wrap up this explainer, I want to leave you with a pretty massive thought to chew on. Earlier, we talked about that unbreakable rule of thermodynamics. Heat always flows from hot to cold, and it never ever stops until thermal equilibrium is reached. Now zoom out and look at our entire universe, full of blazing stars and freezing vacuums. If heat transfer never stops, what happens billions of years from now when absolutely everything in the cosmos finally reaches the exact same thermal equilibrium? If there's no hot and no cold anymore, energy just can't flow. I'll let you sit with that one and ponder the ultimate fate of the universe. Thanks for hanging out with me for this explainer, and keep questioning the physics around you.